The stock market is notorious for its volatility, dynamism, and non-linearity. Accurate stock price forecasting is extremely difficult due to a variety of factors such as politics, global economic condition, unexpected events, a company's financial performance, and so on. All of this, however, implies that there is a large amount of data to search through in order to find patterns, and this is why deep learning is important. So let me give you a brief about it. The ability to process large number of features makes deep learning very powerful when dealing with unstructured data. So stay tuned to the video so that you can witness to predict the stock price of a particular company using deep learning. If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new update or video releases from Great Learning. If you enjoyed this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video for any query or suggestions, and I will respond to your comments.
This session is about applying deep learning models into stock prediction. I would like to largely focus on the concept, how deep learning model is being applied in time series. We would have so far gone through how to apply deep learning models in cross-sectional data. Right? We would have not seen in terms of time series data. So this is what the session is all about. I'm assuming a lot of you would have already completed the time series module, but if not, for those who haven't completed it, I'll anyway start from the basics. So what is time series forecasting? It is actually an attempt to forecast the future values by understanding the past values, identifying repeatable patterns, and forecast the future. If we compare the same to the cross-sectional data, this is no different, right? Even in the cross-sectional data, we do a lot of bivariate analysis, and we build the models based on the patterns we identified from each independent variables towards the target variables, right? Similarly, we also going to identify some patterns in the same time series. Only that here there are no X and Y, there is only one variable, which is time series. And the only independent variable attached to it is time, which is basically the date. Right? That is the only, to put it in simple terms, you will have only one column in your Excel sheet. Right? That is what the time series is all about. So when I said patterns, so cross-sectional data is nothing but the data that you guys have been working on, right? You have, let's say you have 10,000 rows of your customer data, which was collected at different time series, right? Some data would have been collected yesterday and some data some 6 months before, 1 year before and all that. So they are not time dependent. So we collectively work on those 10,000 customers and we do some analysis. So we don't assume any time recency or older data and all that in cross-sectional data. When it comes to time series, it is dependent on the time, right? It has to be sequential. So when I say sequential, if you look at the plots, I have given 4 plots here, which starts from 1970, early 1970s to 1995. And the same goes for the Australian quarterly electricity production. It starts from about 1955 to 2010. Right? So this has to be in an orderly basis. Remember the random stage shuffling and all that, the liberty that we have in cross-sectional data, we cannot do that here. So we will have to depend on the order and we should not be changing that. Right? And when I said patterns, in cross-sectional data, we identify a lot of patterns, like if age is increasing, the insurance premium amount increases, right? These are some of the patterns we identify. And based on that only, our model gives us some prediction. Now, what are the patterns that you have in time series? Right? You don't have any X variable. You have only one column, which has any, let's say if it is a sales data, you have only sales. Let's say monthly sales data of Flipkart for past 12 years, right? So 12 into 12 months. So you will have about 144 data points with you. With that one column, what are the patterns that you can identify? If you plot it against the time, businesses leave some patterns, right? Any behavior leaves with patterns, not just with human, it's all in the business as well, right? So if you look at the first plot, this has a very good seasonality on yearly basis, and also overall it has a very strong cyclicality, right? There is no trend in the data largely. Together, there is no trend, but we can see a seasonality that is there in the data. When we move on to the next one, this does not clearly have much of the seasonality, but we can see a strong downtrend. So the pattern that is prevailing in this series is largely dictated by trend. And here it is all about seasonality and the cyclicality. Looking at this plot, we have the strong trend for the past about 50 years, and we have a very strong seasonality as well. So together, trend and seasonality can dictate about 80% of the data. But if you look at the last one, this is where when you pitch in some real-time scenarios, you get data like this, right? Where you don't find any pattern, any trend, or any repeatable patterns, right? What can you do when you have this kind of data set, when there is no pattern at all? This is where models like deep learning models helps you a lot. It helps you to pick up the noise as well in the data. We will first see basic steps in forecasting. This applies for traditional models, deep learning models, most powerful deep learning models. The steps are one and the same. And this is as well in the classification and regression models we've seen, this is almost one and the same. The problem statement, let's say in terms of time series, what kind of problem statement that can come? I want to forecast the future of, let's say, sales, or let's say the profit of a company. I want to forecast for next 1 year or 2 years. Based on that, the company can plan the budgeting, right? In terms of production, how many, let's say Hyundai wants to forecast how many cars demand will be there for next 1 or 2 years. So based on that, they can plan their production and all that, right? So this is one thing I wanted to say at first beginning of the session itself. This time series has advantage of application throughout any industry or any business that you can pick. And the second advantage attached to it, the data availability will be very easy compared to the other cross-sectional data. It will be readily available in the MIS, and you can just pull it out and you can right away work on building the models. Right? That is why if you see a lot of projects, a lot of startups, a lot of analytics company, they initially focus on building time series forecasting. Right? So that's problem statement. Then we can gather the data, which is quite easy in terms of time series forecasting. This applies for the stock market as well. You can just log into nsindia.com if you're in India, or nizy.com in USA, and you can just right away download the data. It is free of cost. There is no time that is involved at all. It is in terms of seconds you can download the data, right? So that is the advantage of time series forecasting. And understanding the data, here is where we generally use EDA, but understanding the data is where we do EDA in cross-sectional as well. Here we will do a different set of descriptive statistics. I'll show one of the descriptive statistics that one plot can explain the entire EDA of time series forecasting. So we will understand what kind of patterns that are there available in the data, and based on that, we will start choosing and fitting the models, right? And then once fit the model, then we can just evaluate. And what are we forecasting in time series models is just the real numbers, right? Like a regression problem. So what do we do in regression problem to evaluate? We get RMSE, MSE, MAPE and all that, right? So we will apply the same methods here. And more importantly, there also we use RMSE more frequently. Here also we will use the same. And once we are happy with the model, we will forecast the future. Right? Let's say I have 5 years of monthly data. I will have 60 data points. I want to predict for next 6 months. So I can do that. With the model that I've built, the model would have learned the past patterns, and it will tell what are the kind of patterns that you can expect in the next 6 months. Right? Looks charming, but there are some problems. See, these are some of the forecasting models, traditional forecasting models that were there in the history. These are the kind of models that are there for more than about 60, 70 years in the history, right? Like average method, just getting the mean value and saying that on an average, let's say Virat Kohli's average is 50. And if someone asks what is the score that he'll score in the next match, people will say 60, right? 50, I'm sorry, because his overall average is 50. that isn't a simple forecast. The naive forecast is what he had scored in the previous match. We assume he's going to score the same in the next match, right? Seasonal naive is almost like the naive, wherein which if it is a seasonal product, let's say Apple sales, every December we see higher Apple sales. If that is the case, then this month is a December month. We will say what was the last December month sales, right? So, and drift method is giving some amount of change over time so that the business keeps improving every year and month and day, right? So we cannot say yesterday is going to be today. So we will give some amount of increase so that it will keep on going upside, like interest rates or let's say GDP of any country, it keeps increasing with a small amount of change, right? So with just drift method, we can predict that. And exponential smoothing method with just, if your time series has only trend, you can use double exponential smoothing. And if your time series has trend and seasonality, you can use triple exponential smoothing. Right? These are very, very basic models. Don't just focus on the names. These are completely simple models. I'm not getting into all this because these are traditional models. Most of you must have already known if you have done the time series forecasting modules. If not, these are very simple. This is the only EDA image that I wanted to show in terms of time series forecasting. This is a data of air passengers data. And this is the original data. The top of the chart is basically the original data. And we can see there is a strong trend plus very strong seasonality as well. And we can see the seasonality over the time is keep increasing. Right? This is how the real business also, right? Every year, the air passengers keep increasing. And during the festival time, we see strong demand for the aviation. Not even for the festivals, even on the Saturdays, Sundays, right? Weekends, peak hours, non-peak hours, we see the stable seasonality always, right? So that's why we are seeing a very clear pattern in this. But just by looking at the plot, we cannot assume the patterns are going to dictate the entire time series. This decomposition function helps you to split out all the patterns that are available in the data. If you look at the second plot, this only gives the trend that is prevailing in the entire series. This trend is nothing but the 6 months average. Let's say at this level, what is the past 6 months and next 6 months average, which is basically called as central moving average. So based on the past 6 months and the next 6 months, it will calculate the average value and it will keep moving the window. At any point in time, it's previous 6 months and the next 6 months. That average value will be calculated here. So this gives you the clear trend that is available in the data. The next one is seasonality. It calculates the percentage of change at this point compared to the previous point, right? Compared to the previous seasonality. So and the total changes average is the one seasonality change. And if you look at the last one, this is nothing but the residuals, or you can say error, or you can say reminder of the time series, which means whatever that is left after trend has been sucked out and seasonal has been sucked out, all other random values will be displayed here. And we can clearly see the traditional models can only pick these trend and seasonality, right? If they were to pick only these two, they will certainly not include this noise in their model prediction. And we can see some more information is also left in the model prediction, right? In this random values, we can see some patterns also there left out by this decomposition. So if I build a model around these values, probably I'll be leaving these things, right? This is where the need for deep learning models comes in, right? Another model, which is the last model in traditional model, is quite powerful model, which is auto-regressive moving average. We normally call it as ARIMA model, which is nothing but the linear regression, right? We already know what is linear regression. Given the X, what is the Y, amount of change in Y, right? Which is nothing. Auto-regressive means the regression over its own series with its n number of lag values. Let's say in this series, if this is the value, this value is being dictated by the 12 months before the data, right? So if I give a lag value of 12, the regression will take cues from this value and it will predict this value. And it also keeps an average of errors as well. So it calculates an average of errors and it will also add here. So this is an attempt to bring in this residuals into the model. So the model will also learn some more bit of the residuals that is left in the time series. Right? That is why ARIMA is still a traditional model, but quite powerful than the other average exponential smoothing models and all that. Right? We will not get nitty-gritties of all this. Eventually, you will learn quite easily all this. Our agenda today is to apply the deep learning models, how to handle this part, right? How to handle or how to take cues from this residuals. We will be looking at Bharti Airtel, which is listed in Indian stock market, and company which is known for everyone. Right? This company is trading at 525.45 as on yesterday's close. And I have taken data till 29th June, which is 3 days before the present. So using that data, which is this data, using this time series plot, let us predict next 5 days or 10 days what is going to be the trend for Bharti Airtel. Right? As we can clearly see, this is stock market. There is no repeat in trend, right? There is no repeat in pattern. Every day morning is new to stock market, right? So one thing that is guaranteed in stock market is nothing but the randomness, right? Anything can happen. That is the only thing you can guarantee in stock market. Nothing else is guaranteed, right? I've been in the stock market for past 10 years, so I can quite understand that. And this statement holds true. So given that anything can happen today morning, so how can I build the model around it? You can still develop some sense around it. Let's say if Bharti Airtel has moved up by for past 5 days, if the stock is going up, what will be happening on the 6th day? Right? Here you need a human brain to think about it. What if I replace that human brain with a neural network model? That is an attempt of bringing in deep learning models, which is particularly ANN, into time series forecasting model. Right? So we can clearly see there is no trend, and obviously no cyclicality, no seasonality, no patterns that we can see here. Right? So let's see how we can build the deep learning model around it and still predict. So we will start with the neural network. See, ANN is nowhere related to what we are going to learn today. Right? We are going to learn RNN and LSTM, but the base of it comes from the artificial neural network. First of all, we all know it is a powerful model. Why is it powerful model? Because it learns from each data point. Right? If you the next powerful model that we've learned in our academics is random forest, right? And we all know it does not go row by row, right? It compares the column by column towards the target variable, which variable has the largest proportion. Based on that, we split the data, right? We don't learn with each rows and each observation, right? In terms of ANN, we pass on each rows and we understand. We initially assign a weight and we calculate the error and we do back propagation to bring down the error, right? So that is why, first of all, ANN is powerful because we learn from each observation. That is one thing. And the second thing, the hidden layer is what makes the learning very deep, right? As we can see, neural network is simply X values, which is your independent variables, assigned with some random weights initially. And we will apply some activation function and we will calculate the final value, right? And what are neurons here? Neurons is nothing but the parts of hidden layers, wherein which it starts within 0 to 1. And if it crosses a certain value, that particular neuron will be lit up. If it does not cross that certain value, that neuron will be avoided for that particular observation. Right? Let's say I want to eat samosa, and let's say today it is raining, and I also have a fear of obesity. If I eat samosa, I have a fear of obesity, and let's say the shop is not hygienic, whether the shop is hygienic or not. Let's say I have three variables now, whether it is raining or not, Do I have the fear of obesity or not? And if the shop is hygiene or not. So I consider these three factors to decide whether I need to have a samosa or not. Right? Let's say out of all this, I think hygiene is the important factor I consider before entering into a shop to decide whether I have to have the samosa or not. Right. So what I will do, I will give higher weightage to this. Let's say I give 6 and I give about 1 and 1. So these now I will have some values here. If I in my data set, I can just multiply them with the weights, and I can add all these values. I'll get a final value. Right? Let's say I get about 10 here. I pass on this to an activation function. If my decision is whether I'm going to take samosa or not, it is going to be a binary classification, wherein which I'll apply a sigmoid function, because I have to constrain this value within 0 to 1. Right? So I will apply a sigmoid function, activation function as sigmoid function, and based on that, I will decide what value I'm going to get. Is it 0 or 1? Let's say I get 1 here, then my prediction is 1. But this is just half of what deep learning is all about, right? Particularly ANN. This is forward feed. And once this learning is done, we once again compare with the actual data. We have the advantage of trained data with us. So we can compare the same with the trained data. And we do something called back propagation. Right? With back propagation, we have actual Y value and my predicted Y value. So this will give me the difference, which is basically my error. And my objective in terms of back propagation is to bring down this error. Right? This is where we follow a gradient descent method. Let me just, let's say I get error of -5, -4, -3. These are my errors. And probably I'll have to be squaring it, right? We generally square the errors. These are nothing but the squared errors. And how do we achieve the parabolic structure? Just plot this. So here's where we achieve this looks like a big smiley, but this is a parabolic structure. And this is how we achieve this parabolic structure when we plot all the errors. Now, if this value is this side, it means these are negative errors, right? Let's say my error is at this range and my slope is going to be at the downside. When my slope is at the downside, I'll have to increase my weight, right? My actual error is below the actual value. So I'll have to increase my weight so that it'll go somewhere close to 0, right? Close to 0 or above 0. We tend to achieve 0, right? So I'll have to increase the weight. So in this case, I will increase the weight. And if my error is on the right side, which means my error is 5 points away from 0. So I'll have to bring down the weights. Now, this is what gradient descent does, right? It either increases the weight or brings down the weight, and it ensures the error is brought down. While this is being done, there are a lot of methods to do this, but gradient descent is an attractive algorithm where it keeps the learning rate at a lesser pace, right? It is once again a randomness of assigning the weight, right? In terms of randomization, when we give a very lesser learning rate, it keeps reducing the weights. Let's say in terms of here, it keeps reducing the weights in a slower rate. And when it nears to the suboptimum error level, it slows down the learning rate further to a further level. In case of this, it increases the weights, and the rate of increase in terms of weights will be slower when it approaches the suboptimum level, which is actually 0 error, right? This 0 error. This is what, on a nutshell, a gradient descent is, right? So I just drop all this. We spend time on ANN. Now this is powerful model, we can all agree on that, and you would have seen some splendid accuracy in your data sets as well, and even if you apply them on the real time, people get very good accuracy. But what is the problem with neural network is when you work with the sequential data, right? Even though this learn backwards, if I give one customer, let's say one day I predicted my samosa and it gives me, okay, that day it was not raining and I had a fear of obesity. So I did not eat samosa one day. But next day the things will differ, right? Not just if I don't eat samosa yesterday, that is not going to affect my today's decision, right? I will once again see whether it is raining or not, the shop is clean or not. Still, I have fear of obesity and all that, right? So yesterday is completely independent of today. The trials are completely independent. And if you have a data set of 10,000 customers, one customer defaulting does not affect the other, right? So when there is that kind of independency, neural network, artificial neural network will work well. But what if I have a sequential data? When I say sequential data, this is what I mean. It is associated with a time series. I cannot break in or I cannot shuffle it. Right? It has to be on an orderly basis. Some of the sequence data, time series data, let's say sales data, which I've shown here, sentences in terms of writing sentences. Let's say we want to know what Donald Trump is going to tweet next, or Elon Musk is going to say. Let's say he started typing tweet and we want to know what he's actually going to type about. Right? This has to be in a sequence basis, right? Sentences. And same goes for audio, voice transformed between there are a lot of NLP techniques applied in decrypting the audio between the armies and the military and all that, right? So these are all basically sequence data. And once again, the music as well. These are all sequence data. We want to know what the next beat is going to be. Is it going to be a high beat or low beat, or the bass is going to be high or low? If you want to predict that, then the order cannot be changed for that data. So when the sequence is there, the independence is there, right? If the stock has gone up yesterday and today, the chances of it going up will be there, but it will not be higher, right? That is the nature of stock market. Stocks cannot keep going every day. Right? So that is sequence data. This is one more example I can give is, let's say CSK is playing and last 5 matches, we look at their track record, right? Win, win, lose, lose, and win. Based on that, we will predict what is going to be the next match, right? With just one match, if we predict, it will not be better, right? We look for the form of that particular team. This is basically the sequence data. And if you look at the example that I've shown here, I'm not sure if it will be quite, visible or not if you are watching it in mobile. But if you are typing something in your Gmail, let's say here with attaching my resume, kindly, and it will automatically say do the needful, right? It will automatically predict that for you. And this is possible because it is a sequential data, and this is because of an RNN, the algorithm which we are going to learn today. Right? This is once again a neural network model, but works on a sequential basis. Right? There are two kinds of method that are there in RNN, which is many to many, many to one. Let's say if with past 5 days of my data, I want to predict next 2 days or 3 days. Or let's say if you look at this example here with attaching my resume, I'm not predicting the next word. I'm predicting next sequence of words. Right? This is called as many to many inputs and many outputs. And sometimes it can be many to one as well. Let's say I give last 30 days of stock price data and I want to just predict what will happen tomorrow. I don't want to know what will happen next 5 days. I want to know what will happen tomorrow, how the prices will close tomorrow, just one day. Right? The same applies for the CSK example that I gave. Last 5 minutes data is with you. What will happen on the next match? This is basically many to one. Right? RNN really works well with many to one cases. And in terms of many to many, it still works well. As you would have seen in your Gmail, the error will be very, very lesser in terms of prediction. It will really work well. But to start with, when you are starting to learn deep learning models, I would recommend to start with many to one. Particularly in stock market, you cannot keep saying what will happen tomorrow, day after tomorrow, and the day next to that. Right? No one will believe you. And the same applies for the neural network also. It is very hard to keep forecasting. What happens here is the problem with keep on forecasting is, let's say, this is my data and I forecast the next day. This is my next day. And if I forecast the next day, this is something here. What happens here is if I have to forecast this point, my model has to rely on this point also. And what is this point? This is not an actual point. This is my forecasted value. This will have some noise. And if I keep increasing my forecast, what will happen? I will keep accumulating my noise. Right? So you predict noise over noise over noise. So that's why keeping more amount of forecasting is not an ideal practice. Keep it to a restricted level. Right? So this is about sequence data. And how does RNN helps here? RNN is basically a recurrent neural networks. And this basically works in a sequential basis. What we are seeing here is a structure of an ANN, wherein which you give an input value, get the summation of it, the weights and the input value, just add all of them and apply an activation function. Then you will get an output, right? Let's say I apply a ReLU function here. What we are seeing here is a ReLU function for a regression problem. So if the value is 0, it will not give any output. If it is greater than 0, it will give an output. Right? Let's say I've given age, gender, and my salary. What is my insurance premium amount? So I can predict it using the ANN. When it comes to recurrent neural network, let's say yesterday's value or the yesterday's moment will impact today. Let's say stock market, I'll have to use RNN, where the structure is quite different, but it is once again simple. If you take at this level, the input at T is today. This depends on what happened in T minus 1. The amount of change that happened in T minus 1 will be passed on to the today's prediction also. It will be added with the current summation and together it will be given with an output. And this output, this degree of change will once again be moved on to the next day and it will be added to the previous calculation and we will get the output of T plus 1. It is completely on the sequential basis. Let's say if I have 500 days of data, I will have 500 days of this structure. Right? And we can see we are applying a neural network model. This is almost like ANN on each single data point. Right? That's what makes RNN a powerful one. Right? And so this way, the sequence data has been handled once again by using the ANN. The little tweak is we get the cues from the previous day as well. Rather than relying on every single day's prediction, we also get the cues from yesterday's prediction. Now you can understand one thing. Now recurrent neural network needs a data set that has connection between the days. It need not be yesterday only. It could be last week or 1 month before or 1 year before. But the connection has to be there. The dependency has to be there. If that is not the case, then once again applying RNN will not be useful. Right? So this is one of the assumptions that you need to keep in mind before building a model like RNN. And what kind of questions that it answers? Let's say, does consecutive 3 upsides, let's say a stock goes up by 3 consecutive days, will it create a strong upside trend or not? Right? Or the same goes the opposite way. If the stock keeps coming down, is it going to be a downtrend or not? And we are going to also answer whether the Bharti Airtel is in downtrend or uptrend. Right? And of course, a disclaimer here, this is not an advisory or recommendation class. Don't take it that if you apply RNN model, you can keep taking profits out of stock market. This once again involves what kind of data that you're going to give in. When I say what data, what kind of company. I've chosen Bharti Airtel here because of a particular reason, which I will anyways explain during the session. Right? Without that details about the company, if you apply RNN, you have a lot of chance of going into losses. Okay, so don't take it as a recommendation or advice. This is just to teach how to apply this technique on the real-time data. As I already said, the structure of RNN works like this. If I keep it in vector format, if I just bring it in this format, RNN is today's data. This is my today's X values. And I also get the previous value, previous day's vector. And I assign the weights, I calculate the new one. And I keep predicting it. And the today's prediction will move on to become tomorrow, it will become yesterday. And tomorrow's data will be given here. And once again, the prediction will happen. This is basically a cyclical action. Based on this, if you have 500 days, this will run for about 500 times and it will give the 500 days of prediction. Right. So one of the powerful models you can understand now why it is powerful. And the math behind it is how does it operates? Of course, there has to be equation, right? So let's say previous day x0, there will be a value. We will assign some weights and we will find the h0. And from that, we will apply some activation function with weightages. We will find an output value. This is for one particular day. And from there, I will take this change of level of change to the next day. I will just add this value to the next day, and I will also get the next day's input. Together, I will apply the activation function and I'll predict the next day. The equation goes like this. HT, which is this middle layer, which is hidden layer basically, is equal to, this is just an activation function. I'll come back to this. The weightage into xt, this wi into x1 plus the previous day weights, this weight plus a bias. I have not talked about bias so far yet. So we will discuss about bias here. Bias is nothing but a threshold that we set. If that particular neuron does not cross this level, don't activate that neuron, right? So bias is like, as I said, setting a threshold. You make your model little bit tougher, right? Let's say in a pixel, if there are 3 levels of pixel, let's say mid-level and very darker level of pixel and a very lighter one. Right, so let's say this is medium, this is very intense dark, and there is no color at all. Now, if all these are basically neurons, and if I want to activate a particular neuron, I will say if that content within that pixel has to cross a certain level, let's say if I fix a bias of 0.1, there has to be 0.1 gray color in that pixel. Then only I will activate it. Let's say think about an image like this. This is a picture and it has a number 1. If I just zoom this, you will know this image will be break into pixels. And these pixels will be darker and all the other pixels will be lighter, right? All the other pixels will have 0 value and the central part will have 1 here. This will be 1, all the pixels. And there will be some pixels that will be connecting the whiter part and the darker part, which will be on a medium level of gray level, which will be 0.5 of gray color. Right? So neural network just assembles all this data and it will identify this pattern. Right? Similarly, the same applies in the RNN as well. The bias is one and the same for ANN and RNN, where here we set if that image gray color is not above 0.10, consider it as a 0. Some images will be having, let's say, 0.05, right? But neural network should just ignore that. So that is why we give a bias value, so that even a lighter gray level will be ignored. They are not an actual data, just noise in the data, right? So same way we apply some bias here as well. See, stock market will always have some volatility, right? Let's say 0.1% of volatility every day. If I add bias, I will say that you don't consider that 0.1. That is normal in the business. I don't want to make prediction out of it. That is why we fix bias. And we can, now when I say fix bias, we consider bias. We cannot fix bias here. The model will take care of bias and it will calculate automatically. The Adam optimizer will automatically calculate the best bias rate. Right? This way we can calculate the hidden layer. Once we calculate the hidden layer, the y value is nothing but the activation function into the weights that you get here plus the bias. right? So this is the math behind the RNN. This is applied on every data point. We see 3 data points here, which means we are predicting 3 days of data here. And if I have, as I said, 500 days, it will be having 500 network like this, all connected within each other. That's why they are network. We know that. Now, what happens in terms of back propagation here? Now, we said it will keep remembering the past values, right? Yesterday's values will be remembered today. But what if I have a data which takes cues from the past month values, not the current day value, the past month value? The problem will be the more importance will be given to the previous day, but not for some values, some which is there, let's say 1 month before. That is the problem in terms of back propagation. The weightages will keep decreasing when we increase our back propagation. When we start, let's say I have a value today and yesterday, day before yesterday, and I go on to the past. The weightages will keep declining. How it will decline? Let's say, look at this formula. This is how the weightages are calculated in back propagation. Weight W is equal to weight plus delta of change in weight. This delta change of weight is nothing but the learning rate, change in error, the percentage of change in error divided by percentage of change in weight. Right? If this value is lesser, since I go deep into the past, this value will be keep decreasing, right? Because for every iteration, I will bring down my error. When I bring down my error, I will also bring down my weightages. So there is less possibility that I will take cue from this point to the future point. But more weightage from this point will be given to the future point. Right? If dE by dW, which is the change in error by change in weight, is far less than 1, let's say it is closer to 0, then this value will not have any value at all. Then you will have that particular day point's weightage only. Right? So which means this is not taking cue from the deep past, which is basically called as vanishing gradient. Right? We moved on from ANN to RNN because there is no memory involved. And when we came on to the RNN, we now realize that memory is there in the RNN, but it is not that deep. It is able to remember yesterday, but not, let's say, 1 month before. Right? Another problem. So problem after problem. All these days, we would have been under an impression that ANN is one of the powerful model or complex model to understand. But I think by now, you will feel that ANN is better. So great. So this is model training in terms of RNN. Now, how do we take care of this vanishing gradient? Right? My weightage should not keep going down like this. This is where the next technique comes in, which is long short-term memory. And here, what do we do? This is once again layer by layer, like what we saw here. This is first layer, and this is second day. This is third day. This is first day, second day, and third day. I will not dive too deeply into LSTM. This involves some lot of calculations, but they are not complex calculations. They are very simple calculations, but it involves about 4 or 5 lines of equations. Right? I'll just give an top view on this. This is one neuron. Within that one neuron, what are the things that are happening? Long short-term memory, the need for this is because neural network has to take cue from long-term dependencies. Let's say I have a 500 days data. I also want to give equal weightage to the first day of the data, or 100th day or 200th day, any past value. I want to give equal importance to that. Why is this required, particularly in stock market? Is because, let's say, what happens to a stock if it goes up by 5 days continuously? People will start selling it. All of a sudden, next day, the stock price will come down. But once again, it will not once again go up by 5 days, right? It will go into some other different pattern. And after 1 month or 2 months, once again, this might come back to the same pattern. Like every day, it will go up for next 5 days. Now you want to know what will happen on the 6th day. Now that is where neural network can come in and say, I think this is the kind of pattern I've seen already. My model, I've learned that. And based on that learning, this should come down tomorrow. And that is how I want to build time series forecasting model, not on the average, or because average smooths out everything, right? So I cannot always rely on the average. Will you say Virat Kohli will score the average score next month? You will never say that, right? You will apply, let's say if he's playing in England, you will know when was the last time he played in England and what was his score, what was form then, right? You will ignore all the matches played in between. What was his form in Australia, New Zealand, India once again? You will only focus on the current England series with the past England series, right? This is where you need the help of long short term memory. Right? In terms of RNN, you will forget that. Your model will, when I say you, your model will forget that. But here we can give some importance. And how do we do that? Is by using a function called tan h. In your ANN, you would have learned an activation function called tan h. Sigmoid is basically 1 and 0. Relu is basically for a continuous variable. Tan h is basically at a 3 level, which is 1, 0, minus 1. The advantage is if there is a negative trend or negative impact, the degree of change is on the negative side, it will clearly tell you. In terms of sigmoid, it will still fix it within 0 to 1. So you will not know which is negative trend and which is positive trend. In terms of tan h, you can bring that. And how does it work? How does it remembers past values? Let me give you the. So this is going to be the final slide. If you are worrying, are we looking at too many plots today? So this is the function that is happening between one layer to the other. When I say layer, it is between one day to the other. What happens here is the input layer. This input comes from the past degree of change, right? This is past h value, previous day h value, and this is today's input, right? H naught plus x1. That value is my input to the next layer. And here I apply something called forget gate. If previous day's momentum is not related to current day, the sigmoid function will say whether it is related to previous day or not. Let's say 0 or 1. If it is 0, it will be forget here. Right? The model will drop that memory at all. If it says no, it has some value and it has a relationship to today's change, then the next sigmoid function will add it to a function. Right? So whatever values that is not related, it will be forget first of all. And whatever is required will be moved on to the next level. And here is where we apply something called tan h function, the blue one. Here we fix the weightage between -1 to +1. If say, let's say if it is -1, it means an inverse relationship where yesterday, if it has gone up, today it will come down. And if it is +1, it means yesterday gone up, today once again it will go up. Okay? That is what tan h gives you. If I don't apply tan h and if I apply the value right away here, let's say the value is 10, and if I multiply that, it will keep increasing by every day, right? And your forecast will look like something like this. And your actual values will be somewhere here, and your forecast will look like this because you haven't brought them between 0 to 1 or -1 to 1, right? So this is vanishing. Yeah, I'll come back to the exploding gradient, but this is vanishing gradient that I'm explaining about. So once that is added, the value that is required for the model will get multiplied and it will be added to something called cell state. This line that passes through each layer is called as cell state. This is basically the memory of the model. This line will pass through all the days, all the layers inside the model. Right? And once this has been added to the model, it will start giving the output. Okay, so these are the components of it. Of course, when we look at the mathematical part, it will add a lot of sense, but it will be too much. Now, once we see how it has been applied here, and what is the input of the cell state? It is nothing we are calculating here. The input of the cell state is the past calculation. I think someone is using annotate. Can you just remove it? Okay. Okay. So this cell state, the input comes from the previous values and the new value will be calculated here in terms of multiplication. This is point-wise multiplication, and it will be added to the previous memory. If it is an uptrend, then cell state will have an uptrend. Right? So this LSTM has about 5 parts, which is forget gate, input gate, output gate, cell state, and point-wise multiplication. Right? Which is 0.5 function, either it is a multiplication or addition. Now, I did not explain about one more gradient called exploding gradient and how to handle it. Let's say I know so this is sometimes this is not possible, but I'll give you an example. Let's say in my stock, I know very well about my stock, and I can very clearly say only the past 10 days affect my current day. The traders or investors of my stock do not consider more than past 10 days. If that is the case, it is completely not possible in stock market, but it's certainly possible in some other business. Let's say in auction market, only 10 days window, people can buy within only 10 days. So if someone wants to sell, he would have bought only next past 10 days. So you want to know what price he will quote, you can say what was the market momentum in last 10 days. And I don't want to calculate anything beyond that 10 days. That is where you can use something called exploding gradient, wherein which you can pass in a clip. When I say clip, it will remember only the memory in past 10 days. If I say clip is equal to 10, it will remember only the past 10 days and nothing much, right? So that is exploding gradient, but the use case for it is not that good these days. And vanishing gradient is very popular because the computational power and the supporting mechanism is very good these days. Until that, people were using exploding, but these days the vanishing is being used very easily and quite comfortably. And I will explain why vanishing is being used these days, and particularly why deep learning models are into the talk these days. Even though these deep learning models were there for past 5-6 decades, why are they spoken now? Because if you go into your Colab, there is something called GPU, right? GPU board. This accelerator helps you to do powerful computation, which was not possible decades back, right? And only this, because of this, there are a lot of neural network algorithms that are possible these days, right? And my advice, if you are running, always run deep learning in Google Colab. If you are having a lesser RAM size, like say 8 GB or below that, it is always better to go with Google Colab because this offers you about RAM space of 13 GB. And it comes with an advantage of GPU, right? It will be by default none. You'll have to go to the Colab and you'll have to change it to GPU, right? So we will see how to, we've seen the concepts. Let's see how we can apply the same in the data set. So I'm just bringing in the usual pandas, NumPy brothers, and Matplot. I'm reading the data set, read Excel, Bharti Excel. And this is my data set that I have. I just removed all this. This data set I downloaded from nseindia.com from historical prices. And of course, it is free of cost. And it comes with a lot of prices: open, high, low, previous close, last traded price, and what is today's close, right? And my subject of interest is on today's close. And this comes with VWAP. If someone is already in stock market, you will know this VWAP, volume, value, number of trades, and all that. In terms of time series forecasting, you don't have just to predict the prices. You can also predict the number of trades also. Whether a lot of people will be interested in my stock today or not, right? It's not just the prices. With these mechanisms, you can predict the value, what will be the volume tomorrow, what will be the number of trades, will there be crowd, or the number of traders will be increasing tomorrow or not. Everything you can learn and start forecasting, right? Today's interest is on predicting a stock price. So let's just focus on this. So my new data set will be just one column. You can do some multivariate analysis also. This feature engineering is something that I strongly recommend you to follow, most of you must be already doing it. I'm quite sure about it. But if you don't know about it, please start exploring about this, because this is what will separate good data scientists from an average data scientist. Right? The data is one and the same for everyone. The algorithm is one and the same for everyone. Right? You can do some hyperparameter tuning and all that, but still not much of a difference that you can make. The difference that you can make is how well you read this data and how well you bring in some new information. Right? Let's say 5 days trend. I can create a new variable, 5 days trend. What is the last 5 days trend? Is it up or is it down or is it flat? Right? Was yesterday a high volume day? Right? If it is a high volume day yesterday, nobody will look at that stock today. They will move on to the next stock. Right? So if you want to trade, you want to know whether people will come into the market today or not. So I can say high volume, right? 1 or 0. And this perhaps can be 1, 0, or let's say this is 2, 1, and 0. I can create a label encoding also. And I can keep on increasing a lot of feature engineering. At once I went crazy and I built about 100 plus variables. And that is what the difference that makes, right? What are you teaching here? You are teaching the pattern to the data set, to the model. I'm sorry, right? You are getting the pattern and you're giving it to the model. This is just the data. If models are performing well on the data, think about model performing on the patterns. It will really relate to the real business world and it will give higher accuracy, right? And you can strongly rely on the output that you get from the model. Right, so that is basically multivariate time series. We will not be covering that. I hope that is not the same in your academics as well. But the algorithm is one and the same. The codes is one and the same. You just create feature engineering and get new variables and apply the algorithm. Okay. One thing I wanted to say. So I'm bringing in the data set along with pandas pd.read Excel. Of course, this is an Excel file, not CSV file. There is a super cool function called past dates. This helps you to help Python to identify the date by itself. Yeah, and I will be sharing this Colab file to all of you. So don't bother about typing now. Focus your time on listening to this. And past dates is equal to true will help the pandas to realize that this is a date variable and not a numerical variable. And if I mention index column is equal to date, it will automatically become a index column, right? And I get the info of it. We can say all the variables are in either float or integer. The variable that I'm interested is on the closing price of Bharti Airtel, right? So I'm just getting that df close dot plot. This space is there because in the data set that you download from the NSC itself, there will be a space. There will be an intentional space. I think the data engineering team did not see this. So when you enter the close, you must ensure that there is a gap here, right? So length of the DF, I have 496 days of data. And if I had plotted that, this is how the trend of Bharti Airtel for the past 496 days. In stock market, for a year, you will have 250 days, which means I have about 2 years of data. From 2009 of July till now, I have 2 years of data. And we can see the stock has moved from 350 to about 530, 525 levels currently. Right? And we can see there is no seasonality or trend or anything. Of course, yeah, trend is there. Trend is together, it is at the upside. And we will predict whether the current trend is on the negative side or not. Right? It is at the verge of coming down. As we can see, this is the bottom. And if it falls below that, there are a lot of chances it will come down. Let's see what neural network model thinks about this trend, whether it will go up or come down. Right? So I'm creating a data frame. Airtel close is equal to df close. So this is my data set. And I'm resetting it. I have the date with me. So when I just filter that, it will come with the index value also. So the new data set will be having date also. So I'm just dropping the index, resetting the index and dropping the same so that I will have only one column. and I'm just making it as a data frame. Now let's do a train test split. The way you can do is the data dot index location, and starting from 0, I can specify as 0, and I can just leave it as it is, to 480th day. And the test data will start from 480. So if I say 480, it will start from 481, right? 481 to whatever the length of the data. I can specify as 496, but it is always safe to leave it as it is. Sometimes you may not know what is the exact ending of your data. You can just leave it as it is rather than checking for the same and updating here. Right? And what if your test data changes tomorrow? So it is always better to leave it as it is. Right? So I'm giving 480 days to my train and only 16 days to test. Right? I cannot give 70-30% here because I don't want to predict what will happen to Bharti Airtel for next 100 days. Right? That's not going to make sense. I don't want to keep forecasting over forecast for next 100 days. I very well know there will be too much of noise. So I've splitted the data. Now let's do a scaling. See, scaling is not required at all, to be honest, but still you can do, because when you apply some deep learning models, it is going to take some computational power. And if the values are within the range, the computation time will be lesser. Right? So it is always better to scale them, and they don't change the variance in your data set. Right? So doing scaling is not going to harm at all. It can be standard scalar or min-max scalar. I prefer min-max because this is always going to have a positive value, right? It will always be within 0 to 1, x minus minimum divided by max minus min. So it will always be within a 0 to 1. So that's why I prefer min-max scalar always. And scalar dot fit, I'm fitting it on the train data set. When I do this, I will get the max value and the min value of the training data set. Once I do that, I use the same maximum and minimum to transform the train values. And I'm going to use the same maximum minimum of my train data set on my test data set. This is a common pitfall. I think most of your mentors would have already told this. When you do scaling, you first split the data set. You apply the scaling on the train data set, get the parameters. In terms of min-max, you will get minimum and maximum values of train, and you will project the same on the test data set. In terms of z-score, you will get the mean and variance of train data set, mean and the standard deviation, and you will apply the same on the test data set. That is for the case of z-score. Now I'm using the deep learning models from TensorFlow. This is the library for using a lot of deep learning models, Keras and TensorFlow. One advantage in using in Colab is that you don't have to install these libraries. It will come automatically. But when you want to install in your local machine, sometimes you will end up at a lot of errors. It requires some exceptions, and some libraries should be up to date. A lot of dependencies are there. Right? So it is always better to run these libraries in Google Colab. Only thing is you need internet connection. Right? From TensorFlow.keras preprocessing.sequence. Right? Under the sequence umbrella, we have n number of factors, and this is a sequential data which we already know. Right? So from there, I'm generating something called time series generator. This generator helps us to transform the values, and it will save in an array format. Right? We will shortly see what it does. And for any function, if you want to know what that function does, just do help within the same, pass in the function name, which is time series generator, and it tells you what it actually does, what kind of output that you can expect. And let's say this class takes in a sequence of data points gathered at equal intervals, which means on equal, let's say if it is daily, on daily basis, along with time series parameters such as length of the history to produce batches or training validation. Right? So what are the arguments it expects? The original data itself, and what is the length of the data that you are passing in. These are the two things that are required. What this will do is, let's say if I have 100 training data, and I want to give next 15 test values. So together I will have 150 data points, and the last 15 is basically the test data. Now I will have to validate it. I hope most of you know what is validation data set, right? Other than this is like a test data set wherein which we create, once again, we split the data into three: train, validation, and test. Before passing on the data to test, we will pass it on to the validation to once again validate the model. This was the traditional practice, and the same can be followed in time series as well. Right now, so you can go through this generated at your available time. Now let's pass on this. So I have 16 days of my test data. So I will pass on this length as 16. My batch size is 32. See, this batch size can even be 1. If I say batch size is equal to 1, at every iteration, the entire batch will be considered. If I have 496 days, the entire 496 days will be taken. But if I split them into, let's say, 10 or 20 or 32, the computational power will be very, very lesser. If I give 1 at a time, the model has to be run on all the 496 points. But if I give 10, it will run parallelly on all the data points, 50 by 50 by 50, right? So the time it is going to take is very, very lesser, right? You can always play around this batch size. See, this entire neural network, if you run once, you will get different result. And the second time you run, you will get second different result. In your own machine, the same codes, same data set. That is how the neural network works, right? The weight initialization is always random, right? So it is always better to iterate over each batch size and identify which is the better for your model. I started from 1, I kept 5, 10, 20. Normally for larger data set, people give 32. Of course, we don't have a larger data set here, but generally 32 works really well, right? It can be 1 also. It can be anything. It is going to directly impact your computational power and the time. Now let's build a generator object, time series generated, your data set. This expects X data and Y data. And your time series, your data is X and Y, right? So that's why we give scale train, scale train. X is also scale train, Y is also scale train. Length is equal to 16, your test data size. The batch size is equal to batch size. Okay, this will create an object of train and minus length data. Let's say if my train data is 496, 16 days will be removed and 480 data points will be there. And the last 16 values will be predicted. That's why I give length of 16, which is equal to my test size. Right? Now I have the data set with me that is ready for model building. Now let's build the model. So from tensorflow.keras.models, import sequential. And from TensorFlow, import dense, simple RNN, LSTM, and dropper. We'll see what are these. Don't bother about these new terms. If it is new to you, don't bother about it. We will very shortly see what are these. Right? So I brought in the important functions. Let's build the model. Like in sklearn, what we normally do, we first build the model object, then we will fit it on the train data set. Right? We will say model is equal to sklearn.logistic regression, open and close. Right? We will say some parameters and we will project it on the train data set. The same is what we are going to do here. Only that there are some more functions that we will add to the model. Model is equal to sequential. This is my initial model. And model.add, I'm going to add some parameters, which is my algorithm name is simple RNN. And the number of neurons that I give here is 30. So it has to be minimum 16. If I'm predicting 16 outputs, it has to be minimum 16 and it can be anything, right? If I want to keep more layers, if I want to create more neurons, I can create more neurons. It can even be 100 also, but going for more neurons will overfit your model, right? So I just keep it as 30. You can also try with 16 or 20, 25, right? I tried it and 30 worked really well for me. And input shape, what kind of data are you going to bring in? Length, which is the test size, and the number of features. How many features are you going to bring? Which is only one feature. I have only one feature. Right? If you have a multivariate time series wherein which you have 5 x variables and only one target variable, then you'll have to specify them clearly here. Right? X dot shape of the number of rows and the number of columns. Right? Here we have only one column, so we made it quite simple. The next one is dropout. This dropout is nothing but this helps you to overcome the overfitting issue. Rather than learning from all the data points, let's say if I give 0.2, it means it will not learn from one data point out of 5 data points in the past. Right? So that is what dropout is. This helps you not to overfit the model. Right? The default rate is 0.2. It's not just here. The overall dropout default rate is 0.2, and I've just used it here, and it really worked well. And I add another layer. By adding it, what we are doing, we are actually adding layers to the model. This is one layer, and this is my output layer. Dense is basically the output layer, which is just one. Right? I'm going to predict only one data point for every layer. For every day, I'll have only one output, right? So dense is equal to 1. And model.compile, this is where I bring in the back propagation, wherein which optimizer is equal to Adam and loss is equal to MSC. So in terms of error, y minus y square, my error here is MSC, which is y minus y bar the whole square. Right? Based on that, the optimizer will start applying the gradient, and it will change the weights accordingly. It either increase or decrease. So get the model summary. This is my entire model. The model summary, it has 960 parameters, which is nothing but the input shape, the length into features, right? And once the model object is built, then we will put it on the data set, right? This is what we do in sklearn as well. Model.fit the train data set. Model.fit generator. Generator is the object that I've created here with my training data set. I'll just pass it this here. Epochs is nothing but the number of iteration, right? We will, the back propagation, we'll know how it actually works, and we'll have to stop at a certain level, right? If not, it will keep learning. So I'm going to fix a value that my number of iteration is going to be 10 times, right? If you give more number of epochs, your model will overfit. And if you give very lesser number of epochs, your model will underfit. Right? So you'll have to strike a balance between them. You cannot always decide which is a correct epoch. You will have to only iterate and look at the error, and you can see which one is a better one. Right? Essentially, I gave 10 here, and shuffle is equal to false. Why shuffle is equal to false? And this is a sequential data, right? I don't want to shuffle. And if you run it, this might take light of higher time than the ANN. So once I've run it, I can see in my each iteration how the loss is brought down. From 0.14, it has been brought down once again to much lesser level of 0.015. Right? This is my model history. I can get the same by pd.dataframe model.history.history. This function gives you the loss function. Nothing but these numbers. I can just save them as losses data frame, and if I just plot it, I can see the way the error is starting to come down. And if I don't give the epochs, normally how ANN works is, if the error is getting stabilized, the iteration will get stopped. Right? Instead of doing that, I've given manually the number of epochs, and it looks like at the 10th epoch, the error is at the lowest level. Right? I don't want to furthermore reduce the error. If I do that, I will overfit my model. That is why I said, if you give higher epochs, the model will overfit. Right? Now we have built the model. Let us create a batch, and we will test the same. So in my train data set, I will get the last 16 values. If I say minus length, which is 16, it will give me the last 16 values. Right? These are my last 16 values in my train data set. Right? And we will use the same values, and we will predict the next value. Let's say this is 16 value. This is first test value. Let me predict the first test value, which is model.predict, the same that we've learned in sklearn. Model.predict first eval batch, which is basically the first value of this. And this gives me an output of 0.75. So the first actual value is somewhere around 0.79, and this is 0.75. About 4% of error here, but still looks like a good one to me. Now what I'm going to do is, the same way I predicted for first value, I will have to predict for all the 16 values. So I will have to apply for loop, right? That is what I'm doing here. I'm creating an empty list, test predictions, which will save all the predictions like this, and passing in the first batch, the last 16 values, and model.predict current batch for every first value. So it will keep predicting the first value. And this line of function will give me the predictions. I'm not going to spend too much time on explaining this. What happened is, as we speak, this code was there for past 2 years. As we speak, there is already a predict function that can do all this in TensorFlow. Right? I will also share that prediction code after this session when I share this Colab file. So you don't have to do all this heavy lifting. Just like what we do in sklearn, we just predict it and it will do all the data sorting, making it as a data frame or array by itself, right? So we have the predict function with TensorFlow also. So with that, you can do this quite easily. Once we get the prediction, this is a scaled value, right? This is not my original value. So to bring back to the original value, I can use inverse transform function. True predictions is equal to scalar dot inverse transform function, the min-max scalar that I've already saved before building the models, pass in the test predictions. So this gives me these values. So the predictions are 538, 529, 534, and it says the stock is likely to be somewhere around 528 after 16 days. Right, so let's just add this to my test data set. So this is my original test data set, and these are my predictions. And we can see there is a good amount of error, 546, 538, about 1%, 1.5% of error. Here it is 2% of error. Right, 545 minus 534, about 10 points, which is 2% of error. Right, but we can see at the end they are converging together. The error is coming down. But let's just plot the same. And this is the plot of this test value. I'm not plotting the entire data frame. And we can see it has picked up the noise quite well. Only that it has missed out some trends here, but it has picked up the learning has been quite intense. We can understand the comparison. And this is the final prediction. Right? This is my original value, and just the part that we are actually looking here is this part. Now we have 496 days, and we built model only on 480 days, and we predicted the next 16 days, and we are quite happy with this accuracy. Right? Let's build full model. When I say full model, I will learn from all the 496 days, and I will predict next 16 days. Okay. So apply the min-max scalar on the full data set, the entire 496, and create a time series generator like we did earlier. The length is equal to the same 16 days. Batch size is equal to 32. Build the model, sequential, simple RNN, the same features. I'm not going to change anything here. The same model, fit generator, and check for the losses. Once again, the losses are at a minimum level. Take the predictions. These are my forecasted values for next 16 days. I'm just adding them to my data set. Let me just. So full data is equal to pd.dataframe, np.concatenate, forecast.flatten. I'm using flatten here because I will get an output in a 2D array. Right? This is basically in a 2D array. We can see two squares here, right? So this is in a 2D array. I'm just using the flatten function to make it a 1D array. So after doing that, I'm just plotting the full data set. So this has next 16 days trend also. If you look at the original plot, Up till 500, this was the trend, and this is after 500, next 16 days. And it says the stock price is going to come down. And this was up till 29th July. The data I had was till 29th July. So this was, sorry, 29th June. This was the closing price on 29th June. And after that, the stock prices have come down. Right? And that is what is reflecting here also. And I said 29th July. So this is future. 30th July. Sorry, 29th June was the ending date. 30th June, 1st July, 2nd July. And on 2nd July, my model says it should have been 516, but the actual price was 525. Right? There is a 2% error in this model. Right? So this is basically RNN that we have built. And one good thing about this is this was able to pick up the noise. Right? And 2% error is somewhere around you can accept. Okay. Now let's build LSTM model. What is LSTM? It will not forget the past values also. What if this kind of trend was there in the past? Let's say this kind of trend and this kind of trend. This is what we are having here. Right? If that is the case, what will happen? It looks like if that is the case, the stock price will come down drastically. Let's see if LSTM is able to say that the trend is going to be on the downside or not by remembering the past values. Right? And here, this is practically not required, but I'm just giving you, when you work on a very large data set, this is something you need. What is this? When my model accuracy is coming down, I don't want to look at this plot and decide which kind of epochs that I have to give. I want my model to automatically predict the epochs where the error will start to stabilize. Right? So if you look at this is once again from callbacks in Keras function, early stopping. I'm saying in terms of validation loss. In terms of validation loss, if the loss is getting minimized and stabilized, stop the epochs. Even if I given 50 epochs, if the error is down and stabilized at the 10th epochs, at the 10th epoch, the model will stop at the 10th epoch. It will not go up till 50th epoch. This way, I can once again ensure that the model is not overfitting. Right? So, and what kind of level I'm saying? I'm saying if for the next 2 epochs, the validation loss is not coming down, stop the iteration. Okay, so it will wait for 2. It's by default, it is 0. I can say 2. You can, if it is a very large data set, you can say 5 or 10 also. Right? Once again, this length and everything is one and the same. Let's build the generator here. One small requirement for LSTM is that the length should not be one and the same. It should be one data point lesser than that. Right? It does not accept the lost data point. So I've kept length as 15 and I'm building a generator here. Additionally, I'm also building a validation generator. While LSTM is running, it will also have to look at the validation error. Right? Earlier, we did not added this. So we are adding it here so that parallelly my model will also run the validation test and it will stop at the number of iteration where the error is minimizing. And if you look at this model, the way you can build, once again, sequential model.add, this is one layer. To this neural network, I've just added one layer and the output layer. I've not added multiple layers. This is a very simple data set. Right? So I'm bringing in LSTM, 13 neurons. Input shape is length, comma, number of features. Dropout is once again 0.2. And my optimizer is Adam and loss is equal to MSC. See, each parameter that you see in neural network can be tweaked. Right? They are not hard and fast rules. It's not that the dropout has to be always 0.2. If you want to take risk, you can say 0.4 also. Or if you want to say play safe, 0.1. There are different Adam optimizers also, different solvers that are available in Python. And loss function also, you can use map mean absolute percentage error or absolute error, right? You can change over different values. Then you build the model.fit generated. I have built the model object, then apply it on the data set, which is generated. I'm giving 20 epochs. I'm giving higher epochs because I've given the early stop mechanism. So if the epoch is better, then it will stop automatically. And validation data is equal to validation generator. So when this is building the model, it will also look for the validation error. Based on that, it will stop. So callbacks is equal to early stop. Once again, shuffle is equal to false, right? And this says at the sixth epoch itself, the validation error has brought down, and it believes that further epoch is not required, right? So this is the benefit of early stop. What is the difference between dropout and early stop? Dropout is basically to forget something in the past. Let's say if I keep 0.2 percentage out of past 5 values, one value will not be considered for my learning, right? Why am I doing this? Because if my model learns all the fast by 5 days, there is a chance for overfitting. So you can avoid this also. You can run the model without this also. There is no error. But if you want to, when I ran this model without dropout, my model overfitted. So I just used the dropout here. Even when I used this, there was a chance of overfitting. As you can see here, the loss was here and the validation loss was much lesser. Right? There was a chances of overfitting here. So that's why I earlier used dropout and brought down. Earlier it was even worse. So to answer Sunil Kumar, yeah, the scaling is not required. That is what I said. Scaling is really not required, but this is a practice of making. Let's say you work on some data which has 1 lakh values, and it is going to take too much of computational power, right? When you calculate the MSC values will be very large, right? It is only going to take too much of computational values. But if I keep them in a scaling, the values will be, computation will be very, very lesser. That's why we scale it. And as I said, it is not compulsory. It's up to your own wish, right? So the validation loss is attractive. So I can go ahead and predict the same. I'm predicting the same using the same line of codes, which we earlier used. I've also given the explanation here. If you want, you can just go through, run everything, print everything separately and understand what each line of codes are doing. But this is nothing but location, array location, and reshaping the values. Okay. I've done the predictions. I will just inverse transform them. And when I plotted them, the RNN had actually worked really well, but the LSTM is far beyond the levels. Right? It is way out of the league. The actual values are blue ones, and the LSTM is way below that. Let's understand why that is the case. Right? This looks like a poor forecasting. I honestly agree that this is a poor forecasting, but what happens here, let us understand. I'm forecasting the future also. Now I'm okay with this model. I will explain very shortly why I'm okay with this model. I'm going to forecast the future. The same formula, the codes and everything is one and the same. I'm just forecasting, inversing them, adding to the data frame. And this is how my original, the forecasted values are looking like. It says the stock price is going to fall down. And why it is the case? Because see, I can able to interpret this because I know the domain and I don't know this model as well. I know the Bharti Airtel as well. This is something that every day morning when I wake up, I look at this stock. And LSTM, even though this forecast looks weird to you, it has smartly picked up the downtrend that is going to come in Bharti Airtel. I'm not sure about it, what's going to happen tomorrow in Bharti Airtel. But if you look at the past events like this, which I shown earlier, this kind of trend, in this kind of slide, Bharti Airtel never have came up. Okay, only at a far below level it had came up. But other than that, most of the time it have come down. And in terms of memory, LSTM was able to pick up that, and it is actually giving you a downtrend. Right? And this was one of the smart things with the LSTM. And if I had run more epochs, see, when we got this output, I had ran the model with 10 epochs. But here I had ran only about 6 epochs. Maybe if I increase my epochs, look at this, I have only 6 epochs. So if I increase my epochs, probably my model might perform closer to the actual values, right? That is something I can iterate over different parameters, but I'm quite okay with this. I'm going to select RNN as my best model only for this data set. Why? Because we can see more number of times Bharti Atal will go into a range bound, then it will react, then it will go into a range bound, then it will react. Most of the time it is within a range bound. So past 5 days or 10 days values were dictating the next day value. That's why RNN is more than enough rather than memorizing what happened past 2 years before. Right? But LSTM came in additionally and said there is a chance of downtrend, which your RNN was not able to say. Your RNN is saying the stock price is likely to go up. There is a chance that the stock will come down. But look at this prediction of RNN. What does it tells you? It is likely to go up and come down, which was not there in the training data. And it actually worked in the yesterday. It all of a sudden went up and it came down. Right? This was slightly picked up by RNN, but of course, as I said, don't take it as a recommendation. See, you can never forecast anything in the stock market. Right? There are thousands of algorithms, thousands of geniuses that have been in the stock market, but you can never say what will happen tomorrow. But you can build tools to most probably say what you can expect tomorrow. Right? That is why we do all these things. Tomorrow, what can happen? So I will have a probabilistic view on what can happen tomorrow, and based on that, I can take some precautionary actions. Let's say I am an investment banker and I handle a cash of 1,000 crores, and I cannot simply believe my intuition. Right? I need some technical tools to say what will happen or what might happen tomorrow. That is where you can use these kind of deep learning models. Right? And this trend says after 16 days, Bharti Airtel is likely to go to 512 rupees from June 29. So, which means somewhere around July 20, because I'll have to neglect the Saturdays and Sundays. So around July 20, LSTM says Bharti Airtel is likely to go to 512.40. Right? Maybe check the next week or the next to next week of prices. You will understand this and see whether this model is powerful or not. I'm just thinking the prices are likely to come down. Let's see what happens in the future. And this is not in the academics. I'm just giving you another model, which is Facebook Prophet model. This was built inside the Facebook only, and this was particularly focused on very short-term data, like 1 minute data, 1 hour data, 10 seconds data. Facebook wanted to predict how many events will happen in next 1 hour throughout the world. And some employees in Facebook, they created this model, which is called as FP Prophet. Right? Let's not go too much into this. Even the people who have built this have not given complete details about it. But one good thing about this model is it is very simple to apply. It just needs your X variable, which is date, and the close, which is your Y variable. I am saving it here. And date should be saved as DS and close be saved as Y. This is one of the requirement for this library. So I've renamed them. Then just apply the model. That's all. The way you can apply this Prophet change point scalar. This is some degree of change that I'm giving, and daily seasonality I'm giving as true here. Right? This is a daily data, so I'm giving daily seasonality is equal to true. Of course, there is no seasonality in the data, but I'm just giving some parameters to test what is going to happen. And if you get the predictions, just follow this codes. These are very simple. This is the only line where you can predict the future. Think about LSTM, where we gave a lot line of codes, but in FD Prophet, this is simple. Right? These are just customizations. And FB Prophet is also saying that the Bharti Airtel price is going to come down. Right? All the dots are actually the actual data, and within which it have found out some trend. And based on that trend, FB Prophet is also saying the Bharti Airtel is going to come down. My LSTM is saying the same, and my FB Prophet is saying the same. Let's see what's going to happen in next 2 weeks. right? I'm quite sure you will all be looking at that price. Just go to Google, check for Bharti Airtel share price. Let me know how it went. Okay, and this model once again can be decomposed. And when I decomposed it, this is the trend that the profit model has identified. And in terms of weekly seasonality, there is no seasonality. And it says sometimes on Thursday the stock price comes down, on Friday it goes up, right? And daily seasonality, there is not much to look at this. This is a daily data from morning to evening. We don't have hourly data with us, so we'll just have to ignore this, right? So great. And I think this is it, guys. I hope the session was useful to you. I will just run through the questions that I received. I think I've answered most of them. Yeah. So why did I choose this company? Because I know I've been. You will also know for the next 1 month. This stock is always in a range, right? This will always be in a range. There will be some sudden movement, then it will always be in a range, right? If you look at some other stocks, they will not be in a range. Let's say Adani Ports, for that matter. You can select any stocks, they will. So this is also in a range. I'm not sure what kind of, let's say, Reliance Infra, or let's get the Reliance Share, right? They are not in a particular range. They always keep moving. And Reliance Infra, maybe this was in a trend. And right, see, these kind of stocks are always on the move, right? Uh, you cannot predict the same, right? Each share price, someone wants to see the each share price. Once again, this is always on the move. This is not on a break even range, right? It will always not be within a range. You see, you can also predict ITC. ITC and Bharti Airtel these days are one and the same, and we can see it will be in a range, then it will move, then once again it will be in a range, right? You can apply the algorithm on ITC also, and I applied it, and it said ITC is also likely to come down. So that is the reason I selected Bharti Airtel here. But you can ask me one question: what to do if my stock is moving all the time? Let's say I'm not sure if SBA is right. SBA is also moving. It is always in some trend, right? If that is the case, what can I do is I'll have to create a stacked model. I will create another layer of model here. Let's say I will say model.add. See what is hidden. Why do we use hidden layer? Because our learning has to be deep, right? So for a data that has too many noise, you need more hidden layers, right? So that is where you can add another layer of LSTM. Then you run the model, right? For this data set, I did not require, but if your model has too many noise, or if your data set has too many noise, you can use the same. Right? By this, this is basically called as stacked LSTM. I will just thank this. This is basically stacked LSTM. So you are further deepening the learning so that the model will pick up that noise also. Right? So yeah, some technical indicators, let's say you can take, see, the NSE is starting to give a lot of technical indicators by themselves. If you look at this, VWAP itself is a technical indicator, and give it another 1 month or 2 months, you will get all the indicators in this data set itself. Last year, only these values were not there. If you get the historical data, you will only have these. Right? You would have seen these data in the business line paper also some years before. So that is the thing. Some good reading resources for LSTM. In terms of underlying math, I would recommend Machine Learning Mastery. This website is very, very good. Not just for, I guess this is like, I'm not promoting this page. So let's say, this person I think I've always admired, and he talks each model from the scratch, right? You can also build logistic regression from the scratch, random forest from the scratch, right? You rely on the model function, right? From sklearn you will just bring in the model function and you will right away build it, right? But if you build from scratch, you will know the nooks and corners of each models, right? So this guy would have built each model from the scratch, and he is very good for understanding the LSTM also. You want to learn linear algebra, you want to learn hypothesis, you want to learn probability, I think this guy is very good. So I would recommend this.
If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new update or video releases from Great Learning. If you enjoyed this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video for any query or suggestions, and I will respond to your comments.